Today, we are going to understand a concept which is very important for advancing to topics like regressions and other parametric analysis. In most regression analysis, our objective is to find some parameter matrix beta, which governs the data generating process. Most often, we do not have a definitive idea about the population distribution, yet statisticians have devised interesting techniques to estimate these parameters without knowing much about the population. Let's consider an artificial population. In this case, we know that the population is from a uniform distribution. The population consists of 5 values, 2 to 6, each occurring only once. So each value has a probability of 1 by 5 to be drawn independently in a random draw. We can express population distributions using tables, formulas, or graphs. Here is a graphical view of this artificial population. We can see that both the true population mean and median is 4. Now, let's imagine that there are 5 circles inside a box. We can draw one circle at a time, look at its value or the number on it, and then put it back inside the box. Then we draw one circle again and note its value. We can do this exercise repeatedly, considering a sample size of 2 for our experiment. This would be a repeated sampling. In such context, there are 25 possible pairs of values that we can get. For example, I start by picking a circle and get a 2 on my first draw. Then I put the circle back in the box and pick another circle to complete the pair. I get the number 2 again. Then my sample would be 2 and 2. So for my first circle, I can get 5 different values, and similarly for the second circle, I can get 5 different values. So there is a total of 25 different possible combinations that I can have in my random draws. So for each of these draws, we can calculate the sample means. For 25 possible samples, we get 25 different sample means. We used symbol X bar to represent sample mean. Since now we have 25 sample means coming from different samples, each having its own probability of being picked, we can demonstrate this in the table. Now what we have is a sampling distribution of a statistic, and that statistic in this context is the sample mean. A statistic is a random variable when derived from a random sample. That is why we have a distribution of its possible values with their associated probabilities. We can also calculate other statistics like the median and get a sampling distribution. But we most often estimate the mean because it is both an unbiased and a consistent estimator of the population mean. We can show this graphically as well, the same way we visualized our parent population. We can see that the possible outcomes of the sample mean is distributed normally with its center being at the population mean. The larger the sample size, the more normally it is distributed, and there is less uncertainty about the true parameter being located at the distribution center. Notice that we did not have to use any information about the true population's distribution or its true parameters. This idea of sampling distribution, that by repeated sampling we can estimate certain statistics like the sample mean and infer about the population without knowing the data generating process, helps us go ahead with different parametric estimations we do in econometrics. We can do the same exercise with n equals to 3, in which case we would have 125 different mean values for 125 possible draws. And we can see that increasing the sample size increases the tendency of behaving like a normal distribution. If you have noticed, you can see that both the sampling distributions with n equals to 2 and 3 have a lower bound of 2 and an upper bound of 6. And both of them are centered at 4. But the graph of n equals to 3 has relatively thinner tails than the previous one. This implies that the values closer to the center of the distribution have a higher probability of being picked in the case of n equals to 3 when compared with the previous one. Let's now connect the idea of sampling distribution to that of linear regressions. Let's think of a situation where we want to know the average height of a country's population. This hypothetical country has 5 provinces. Since it is not feasible to ask every person in the country their heights, and there is a limited budget, we decide to survey 3 people from each province of the country. We do this survey 3 times within the year to create a repeated sampling. Doing this in the month of January gives us 15 heights from 15 people. Likewise, we get 15 more observations in the month of April and 15 more in the month of August. Now we are done with the survey and the field team has sent the data for analysis. Just as previous, we can create a sampling distribution of average heights. This time let's do this by each province. Plotting the distribution shows us that it is centered on 6.954. So with reasonable confidence we can infer that the population mean height of the country is 6.954. Okay, so what if we took the average of all the raw height numbers instead of averaging them for each province? This would also give us a similar number, 6.956. Now let's think of this as a survey data of 45 respondents. How would we estimate this using regression? If we regress the heights on just a column of constant once, we get an OLS estimate of 6.9556. We can see that the coefficient estimate is the same as averaging all the raw height numbers. If we wanted to retrieve the average height of each province, then we can regress the heights on a constant and 4 dummy variables for any of the 4 provinces. Here are the regression results. The coefficient of the constant term is now 4.44, which represents the average height of province E, the one for which I did not include a dummy. For province A, mean height is sum of 4.44, the estimate of the constant, and 3.44, the estimate of the dummy for province A. So we have 7.88 as the mean height of province A. Likewise, we can verify the mean heights for other provinces by comparing with this table. Now to conclude, here is a little simulation of sampling distributions in the context of increasing sample sizes. Here I have taken data randomly from a uniform distribution with 0 lower bound and 1 upper bound and computed means for each draw with 3 different sample sizes. In the first graph, for a sample size of 50, look at the bounds of the distribution. It ranges from 0.4 to 0.6, and it is centered on 0.5, but the draws are quite scattered. In the second graph, for a sample size of 100, now the bounds are 0.425 to 0.575, and the shape looks more like a normal distribution. This one has less uncertainty and more precision. Finally, the last graph, for a sample size of 500, has a range of 0.46 to 0.54, and the values are tightly packed around the true mean. So that's all for today. I hope you enjoyed the video, and I hope you are all having a good time staying home. See you all in the next video.